So here's some other examples of guesses that we might have to adjust. Okay, so here's a non-homogeneous second order differential equation. So let's, as usual, look at the homogeneous one. So we got y double prime minus 8y prime plus 25y equals 0. And so the characteristic equation is r squared minus 8r plus 25 equals 0. And then can we factor that? I don't think so. So we need the quadratic formula. Negative of negative 8 is positive 8, plus or minus the root of 64 minus 4 times 1 times 25 is 100 over 2 times 1 is 4, plus or minus, and then this is the root of negative 36, so it's 6i over 2, which is 3i. Okay, so then our general solution to the homogeneous part is c1 e to the real part 4t cosine imaginary part 3t plus c2 e to the 4t times sine of 3t. Okay, then we look at the non-homogeneous one. We need a particular solution. So we make a guess. Y equals, I have an exponential times a trigonometric function. So that's going to be a1 e to the 4t times, and then this is a2 cosine 3t plus b2 sine of 3t. Once we expand it out, we're actually only going to have two coefficients. So this is going to be a e to the 4t cosine 3t plus b e to the 4t sine of 3t. And now the problem is that these are both solutions to the homogeneous differential equation. So what's going to happen is what happened a couple videos ago. If you try to plug this into the differential equation, everything would cancel out and we would get 0. We could never get e to the 4t cosine of 3t. So we fix our guess by multiplying through by a t. So this is a bad guess. We actually do a t e to the 4t cosine 3t plus b t e to the 4t sine of 3t. That's the good guess. Unfortunately, it makes it more annoying when you take derivatives. You have to do product rule. But you can do it, and you'll get eventually two equations, two variables. The t terms will all cancel out because of the stuff from before. You'll be able to solve for a and b, and then add that to the general solution to get the general solution to the non-homogeneous differential equation. Okay, and then one more example of something that might need to be fixed. Y double prime minus 3y prime plus 2y equals t squared e to the 2t. So let's look at the homogeneous version. We get y double prime minus 3y prime plus 2y equals 0. Characteristic equation is r squared minus 3r plus 2 equals 0. So r minus 2 times r minus 1 is 0. R equals 2, or r equals 1. So then the general solution is going to be c1 e to the 2t plus c2 e to the 1t. This is the nicest version where you have two distinct real roots, right? Okay, and then let's see what happens to the non-homogeneous case. Non-homogeneous. Our initial guess is going to be y equals, let's see, you have a quadratic polynomial times an e to the 2t. Let's put the e on the outside. So a1 e to the 2t times a2 t squared plus b2 t plus c2. And then when you expand it out, you only have three coefficients: a t squared e to the 2t plus b t e to the 2t plus c e to the 2t, right? And this looks like it's going to be fine, except for this one term is going to be a solution to the general homogeneous equation. So you actually do have too much stuff canceling out there as well. We're not going to try it, but it's not going to work. So what we need to do is we need to fix our guess. And we just multiply the whole thing by a t also. So you get a t cubed now, e to the 2t plus b t squared, e to the 2t plus c t e to the 2t. And now we check. None of these terms are similar to these terms. So we're good. If they were, keep multiplying by t's until they're not.